Okay, anybody have any questions they wanted to with cards? What? Do you have a card?
I have a question.
Okay. All right.
I have a card written out.
Vinny. What?
Can we go over one of the questions you got past that?
Yeah. Can I guess which one?
Yeah, I guess.
Yes. So, is it that one?
I got it right. You guess. You got it right.
So that's the one, Vinny? Vinny, yeah, that's the one. Okay, so what happens here? And nearly everyone had the Grignard attack the carbonyl to make the product, which was not correct. Brian? So we have to be careful that our molecule, whenever we react a Grignard or any strong base, that there's no deprotonatable hydrogens in that molecule. So what would be, let's just go back and review for a moment, what would be the hydrogens that get deprotonated by Grignards? Water, alcohol, amines, NHs, that's alcohols, ROH. What else? What else has acidic hydrogens? Carboxylic acids. Right? So you have to make sure that the molecule doesn't have that. And in this case, you can call it a trick question if you want, whatever. But the OH is going to be deprotonated by the Grignard so that you would end up with an O- and a CH4, right? Because CH3 plus a hydrogen. And then when we add the H plus H2O to that, the final product would be the original, which is with the OH. So you have to be careful that those molecules are not the ones that are reacting. And if you look at the exam, you'll see old exams, I always ask, Grignards with something that's deprotonatable. So take a step back before you start adding it. Kevin?
I'm just kind of confused how you would even end up with a CH3 minus Grignard. How did you get that?
You don't like a CH3 minus Grignard?
Because you just start out with an allergen attached to that.
What's wrong with that?
Oh, never mind. I was thinking, I don't know what I was thinking CH4. I don't know why.
No, so you can make a Grignard, which means you'll make a C minus by reacting any bromide with magnesium. Now, here's something else that I took a lot of marks on your homeworks for. What is this magnesium? No, it's magnesium metal. So there's no 2 plus until it gets to this stage where now it's 2 plus with a 1 minus bromide to give it a +1 overall charge. So it's magnesium metal. It's not magnesium 2+. And I saw a lot of Mg 2+. It's Mg. That's it. Just Mg. Benny?
So the final answer,
The final answer would be these two. That would have been the final answer. Josh?
could you go over epoxides?
Grignards with epoxides.
I was very unsure on which side the concluded.
You and others. So let's talk about epoxides in a general sense. Here's an epoxide, unsymmetrical epoxide, A and B. Let's go through a whole series of reagents, and you can tell me what the nucleophile is, and you can tell me where the nucleophile should add. We'll start with that set. Okay? So, pull out your cards, because we'll make this interactive. Although you'll have to tell me what the nucleophile is. Because there's no card for that. And your choices are A, B, or if it's 50-50, C. Okay? So let's start with CH3, H plus, CH3OH. What's the nucleophile going to be in that reaction? Before we get to where it attacks, tell me what's the nucleophile in that reaction. CH3OH. Right? The entire neutral molecule is going to be the nucleophile. So CH3OH is going to be the one that adds. So now how does it add? Does it add to A or B? I don't know. You hold up your card. Make a choice, hold up your card. So where does the methanol add for the first set of reagents? A, B, or C if it's both equally? (14 to 9A). It's not a very large margin. 14 to 9A. No. It's going to add to B. Why is that? Good question. That I should be asking you. Why is that? And that somebody could tell me. Let's take our epoxide. Let's write out the first step of the mechanism. Any mechanism that involves acid in the reagents. What's going to happen when the epoxide reacts with H+? First step in the mechanism. Protonate the oxygen. Okay, so I protonate the oxygen to make an oxonium ion. Now, I know this goes back to last semester and even farther back. Well, last semester's far enough. But what's going to happen is the oxygen's not going to be real happy with the charge, so it's going to push the charge, the +1 charge to the 2 carbons. And they're going to share that charge. Okay. So remember that the next step is for the nucleophile to to come in and add to the carbon with, okay, this is a neutral nucleophile. It's going to react with the carbon with the what? Of those two carbons with delta positive charges, it's going to react with the carbon with the most. How about charge? How about in terms of charge? The one with the most delta positive charge, or the one with the least delta positive charge? All right, the methanol is a nucleophile. In the chemistry world, that makes it electron rich. In the chemistry world, the electron rich must give to the absolute poorest, the absolute of the electron poor. Okay, rich can't give to rich, poor don't have anything to give. You can take that to your social justice class and compare the chemistry world to the other worlds. The nucleophile's got to add to the most electron poor. So that's the one with the greatest delta positive charge. Now, which one is that going to be? Is that going to be A or B? You already know the answer. B, right? Now, why is B? Now we're getting back to why, to the question, why is B the carbon that has the greatest delta positive charge? Vinny?
With the methyl attached, it has more of these protons.
No. Yeah, I like the methyl. The methyl plays a role, but not protons. It's, Brian? Yeah. Which does what? It stabilizes it. If I put quotes around and said, what kind of carbocation is A? If I put a full positive charge on A, it would be a quote, what kind of carbocation? Primary. Now you might say, well, that's bad. Yes. But this still bridges. What kind of carbocation would B be? Secondary. Which one of those two carbocations is more stable? Secondary. So now I'm reacting a nucleophile with the carbocation. That is an SN 1 or 2? 1. It's SN1 because it's carbocation. So which carbocation does the nucleophile add to the fastest? The most substituted, the most stable. So the methanol will add to B. Because when I add acid to the epoxide, I change the mechanism to make it look like, quote, SN1. Now, the reason I'm saying, quote, SN1 is because I'm not dissociating into a pure carbocation. And I know that's the case because the nucleophile in the OH group will always be, at the end of this reaction, the nucleophile in the OH group will be trans. And the only way that nucleophile and OH group are 100% trans is if that triangle stays intact. If I broke that triangle apart, I'd get 50-50. So that's the reason why I'm quoting SN1. What I really mean is when you add acid, the nucleophile has to add to the most substituted carbon. Does that make sense to everybody?
If it were a quote tertiary carbocation, would it also give it sterics?
Nope, sterics are not part of SN1.
Okay.
Sterics are not part of SN1. It's stability of carbocation. So that's the thing. Yes, it's attacking from underneath, but sterics has nothing to do with it. It's all about the stability of the carbocation. So if I had a secondary carbocation on one side of the epoxide and a tertiary on the other, the nucleophile is going to add to the tertiary side. Paige? That's a good question. We'll get to that. So sterics is going to play a role when I don't add acid. If I just have the nucleophile attacking the epoxide. But in this case, whenever there's H+, you got to protonate the OH first. Once you protonate the OH, it pushes the electron density down to the 2 carbons, makes it SN1. Nucleophile has to add to the most stable carbon, to the most substituted carbon. Benny?
So after the files does it end up breaking?
Yep. So this comes in, adds to B, the OH swings over, and we end up with the OH here, the OH with the CH3 here, with the plus charge, and then it's going to lose the H+, because remember, acid's a catalyst, so it's got to be regenerated in the last step. Now I've got an OCH3-, but the OCH3- added to the most substituted carbon. And if this was part of a cyclohexane ring, I would have to put bold and dashed wedges in place to show that it added 100% trans. So does that make sense to everybody? The thing you have to remember is, if I come back here, well, I'll draw out a summary diagram. So H plus H2O. If I added H plus H2O to that epoxide, what's the nucleophile? H2O. And H2O is going to add to which carbon? We all agreed B? Okay. So anytime you have acid involved, the nucleophile will add to the most substituted carbon of the epoxide. And I know at least one person has talked to me in terms of memorizing which group the OH swings to. I mean, that's your system. If it works, I'm not going to mess with it. But it's really that the nucleophile's adding to the most substituted carbon. Right, so anytime there's acid. So if I would have gone back here and I would have said, well, how about HCl? If I had HCl to the epoxide, what's the first step? Protonate the O. Where's the Cl going to add? To the most substituted carbon. Okay, so that's the critical part. Acid, nucleophile adds to the most substituted carbon. Sam?
So if you only add CO minus, then it's just going to go to A?
Yes. So now we have to deal with the other alternative, because anything that adds acid goes to B. But the question was, where does the methyl group, or where does a methyl CH3 go? Which would be the same question of, where does a methoxide go? Where does a hydroxide go? Where does a chloride go? Okay. So my first question is, if you're adding CH3- to the epoxide, what's the nucleophile? CH3-. So CH3- now is a strong nucleophile. The mechanism switches because there's no acid. So it switches to SN2. So with strong nucleophiles with negative charges, we now go to an SN2 mechanism. I go back to last semester. Let's see, what was reactivity in SN2 in two reactions built on? Steric hindrance. So this is where the steric hindrance comes into play, is when you have a negative, strong nucleophile, no acid. So now that strong nucleophile has SN2, it looks, it says, okay, I got to do this SN2. Which carbon is the least sterically hindered? Carbon A. And so it comes in, attacks carbon A. Again, from underneath, the O minus switches over, and I end up with that alkoxide. And then what do I do? Then I add the H plus to protonate that to make the alcohol. Because when I do that reaction, I'm gonna write it this way. I'm gonna write it Grignard plus epoxide, and then over my arrow it's going to say then H plus H2O. So it came after the reaction. Because if I added acid first, it reacts with the negatively charged nucleophile. And so in this case, if I added H plus first, that'd be great. I'd protonate I actually don't even know that I would protonate the epoxide. Because the first thing I'd protonate is the Grignard and kill it. So by the time I got around to protonating the epoxide, there's nothing there. Because the Grignard's already been taken care of. So here's kind of the summary. So the summary kind of looks like this. Strong nucleophile is going to attack the least substituted carbon. Anytime I add H plus, that nucleophile is going to add to the most substituted carbon, which in this case would be, after it gets protonated, it would add to B, the way I've written the molecule. Right, that's something like what I wrote for somebody this morning, right? So that's how you can think of it. Strong nucleophile, and we can add. We can add more stuff. We can say this would be SN2, this would be SN1. So that's the critical part of epoxides. Because now what it does is it gives me the opportunity, if I needed to add a Cl to A or B, I could say, okay, I want to add a Cl to A, do Cl minus first, then H plus. I want to add the Cl to B, HCl. I want to add a methoxide group or any kind of alkoxide group or alcohol. Alkoxy, the negative charge, A, acid, and alcohol to B. But Grignards, so Grignards, and also your NaBH4, which I forget. NaBH4 is what? What is it? It's an H. It forms H minus. It's sodium borohydride. I know that. Or LiAlH4. Those are both sources of H minus. So you could do the same thing. Have an H minus, add to A.
Was it one of the 4 equivalent?
Yeah, when you're reducing carbonyls. So in this case, it's only adding one H minus. Right. So we have a lot of choices for opening epoxides, but that's the basics. Acid, nucleophile most substituted, negative nucleophile, least sterically hindered. Yeah.
Do Grignards and carboxylic, when they react with carboxylic acid, do they always give you two products?
Yeah. If you react to Grignard, if you say if I give you this problem where I say I'm going to give you CH3 minus MgBr plus CH3 C double bond O OH, and then I'm going to say then H plus H2O. I mean, my over-under, if I give you this problem on Friday, is probably about 20% will add the methyl group to the carbonyl. Right? Even though that we've said don't do that, it's still about 20% would be my guess. It will deprotonate, so it'll form CH4, and then it'll form the deprotonated carboxylic acid. And so then when we add the H plus H2O, we protonate the carboxylic acid, or carboxylate to form. So the final products would be those two. But it always forms two products because the Grignard deprotonated. Okay. Everybody okay with that? What else? I'll just take these two hydrogens away. Notice that the reactions, that we're doing kind of can be broken up into sets. I think last year I just kind of set it up. I put a molecule in the middle and then I just drew arrows around it like a wheel. So we do have these relationships between the reactions. So here's another one we could look at. I'm going to start with an aldehyde and an alkene. And what reactions am I doing? What kind? In every reaction, I'm doing a variation of a reduction reaction. Right? I'm adding hydrogens to all three of them. So I'm doing three different reduction reactions here. So in one case, I reduce the carbonyl but not the alkene, or the alkene but not the carbonyl, or both. Right. So anybody want to give me a reagent that I might use for one of those three? Josh?
For the one all the way to the left is a H2.
So H2 and rainy nickel. Now that's the reduction reaction that we learned this semester. Last semester we learned H2 and what? Palladium or platinum. Where would that one go?
Middle.
Middle or right? for H2 with palladium or platinum? Right? Middle? Do we need to vote? Or are we guessing at this point? Yeah, that's not good. I mean, if it was Thursday, that'd be even worse. But it's still Wednesday. I mean, you still have 48 hours. There's no triple here. And that's the danger at this point. At this point, there's a lot of reactions that look the same, right? And they're just going to look more alike as time goes on. So you've got to figure out a way to differentiate them. So where am I? Well, that you have to remember exactly. I mean, you just have to memorize them, right? Or remember the basics. Right? Hydrogen gas and a metal adds 2 hydrogens to the multiple bond. It depends on what multiple bond I'm adding it to, whether it's double or triple bond, or whether it's a C double bond O. So where's the H plus? Where's the H plus in the palladium going to go? Middle? We all in agreement of middle? Okay. And then what goes to the right? So what reduces the carbonyl but not the double bond? Brian? Some source of H minus. Whether it's sodium borohydride or lithium aluminum hydride, that will react with the carbonyl but not the double bonds. Okay. So the card says, go over a reduction reaction using Raney nickel. This is a value-added problem because it gives you more, right? So the first question is that H2 will add to a multiple bond, a double or a triple bond. The triple bonds are a whole other series of problems, right? Because I could have the triple bond going to the alkane, going to the cis-alkene, and going to the trans-alkene. But let's worry about this problem first. So which double bond is more stable? The carbon-oxygen double bond or the carbon-carbon double bond is more stable? It's actually the carbon-oxygen. So the carbon-oxygen double bond is really stable. Now, I could go back and relate that because remember when we added a nucleophile, a minus, a Grignard, an H minus to the carbon-oxygen double bond, and we formed the O minus? What happened next? It depended, right? Because it wanted to reform the carbonyl to bring the pair of electrons down and kick something off. If it could, it did. If it couldn't, it stuck. So I probably said at that point, carbon-oxygen double bonds are very stable. And they're more stable than carbon-carbon double bonds. So what that means is things that are more stable are how are they in terms of reactivity? They're less reactive, right? And that's easy to remember because that rule holds for people. Right? The more stable, the less reactive. Although there's a constant continuum of stability and volatility with people. But again, another class, you can go discuss that in. So C double bond O is more stable than carbon-carbon double bonds. So the purpose of Raney nickel is it's a more powerful catalyst. So not only will the hydrogen be reduced add to the double bond and reduce it, But with rainy nickel, it will reduce the more stable C double bond O. So in this case, the rainy nickel adds hydrogen to the double bond, carbon-carbon double bond, and the more stable carbon-oxygen double bond, because this is more reactive. Brian.
So then how is it that H minus doesn't reduce the less stable double bond?
Well, that's a good question. I'll get to it. Using the same fundamentals that we've used all year. Okay. So over here then, H2 and palladium or platinum, which is the run-of-the-mill catalyst, it reduces the carbon-carbon double bond, but it isn't reactive enough to reduce the more stable carbon-oxygen double bond. So H2 would reduce either, it just requires the right catalyst.
So platinum or palladium is not strong enough to reduce the carbon O bond.
Right. So it's not strong enough to reduce the carbon-oxygen double bond, and that's why we have to use this specialized rainy nickel that all of a sudden is more active. That's a better catalyst. Right. Is everybody kind of with me there? So that's the purpose of rainy nickel. It's to reduce carbon-oxygen double bonds, but if there's a carbon-carbon double bond in the molecule, it's getting reduced too. Now, what about the H minus then? Well, if I said, what is the same about H minus and a carbon-carbon double bond? They are both blanks. They're both nucleophiles. They're both electron rich. Right? And what do we know about chemistry? Nucleophiles only react with electrophiles. So if you have two nucleophiles, they won't react. So the H minus will not touch the double bond because they're both nucleophiles. You say, well, then what's different about a carbon-oxygen double bond? And what we say is that in that case, because the elements aren't the same, the carbon-oxygen double bond has the carbon with the delta positive charge. So now what does it have? It's got charge, and so this carbon is now an electrophile. It's electron poor. So now the H minus can come over and add to the carbonyl. In the carbon-carbon bond, whoa, what just happened? How did it get so big? In the carbon-carbon double bond, they both have the same charge, so there's no electrophile, no nucleophile. Or there's no electrophilic part, nucleophilic part. So that's how we have to think of those kind of three reactions together. Kevin?
So after the H minus adds, it makes an alkoxide, right? So then how does it get protonated?
Well, remember that basically if we have an H minus reacting with a carbonyl, the first step is that the H minus is going to add to the carbonyl group. And I'm going to make an O minus. So then a couple things could happen. If these are both alkyl groups or one alkyl group and one hydrogen, the reaction's done, right? Because as try as it might, this thing wants to bring its pair of electrons down. Nothing can leave. So it's stuck. So it just hangs out there until I get some acid and water, and I dump in my acid and water, and now I form my alcohol. And that's the same thing that happens when you react to Grignard with a carbonyl. The O- tries to reform the carbonyl by kicking something off. If it can't, it just waits for the H plus H2O. So then you'd say, well, what molecules have we had so far where the O- can come down and kick something off? Well, it's not an alkyl group and it's not an H because those don't act as leaving groups. So what could I put here? A what? Put a halogen there, yep. So acid chloride. Or I could put an OR group there. Or later on, an OH. So when these groups can leave, they get kicked out. And that's how we do the reductions of acid chlorides all the way down to primary alcohols. That's how we do the reduction of an ester where it splits apart into the two alcohols. Primary and then whatever the alcohol part was on the other side. Vinny?
So you're saying that the Cl would leave, but nothing that happens to the double bond?
It'll reform. So the H minus comes in. I end up with my O minus and then my H and my Cl. This molecule wants to reform the double bond because it's so stable it brings a pair of electrons down. It now sees a chloride can leave, so it kicks off the chlorine. And now we end up with the double bond and now with the H there. And then this is where we remember that lithium aluminum hydride and sodium borohydride have 4 H minuses. So as soon as this step occurs, my second H minus comes in and adds to then give me an O minus, which is now stuck because nothing can leave. What else?
A lot of your previous exams that are posted, a lot of it, like, I don't really see a lot of mechanisms. It's like a lot of
You
naming and
might not be looking at the right ones.
it says exam one.
Exam 1's for second semester. There might be a little bit of naming, but there's at least as much mechanisms. I mean, usually the first problem is always the first set of problems is always a mechanism problem.
Yeah, then I'm looking at the one. Never mind.
You might be, if you're looking at exam 1 from last semester, we didn't know what mechanisms were.
Yeah, just tons of.
So yeah, you want to look at the CH222 exam 1s. In the last 5 years, we'll have everything but alkynes.
Right. I'm
Right.
Okay.
But I'm going to give you some mechanisms. I'm going to give you some reactions to give me products. And then I'm going to give you probably some reactions for you to give me the reagents over the arrow. And there was one test where there's numbers along with the structures. That year I gave the students a sheet of all the possible reactants and products of the entire exam, and they could write down the number instead of write the structure out. But I don't do that anymore. I did that one year. It was sort of a multiple choice. It was a complicated multiple choice because you basically had every answer, including all the wrong answers, to choose from. So when you see that, it's the structures that are in the boxes that are the correct answers. Brian?
Could you do one example, like in the homework where you have a molecule and then the reagent that you use to form the next one is an epoxide? So like how to, if given reactant and product, how to know what the epoxide looks like?
Okay, so
it was like a ethyl with the VR at the end. Or sorry, on the cyclohexane.
so an CH2CH2Br,
Yeah.
something like that. Okay.
And then the product was that plus some more and alcohol on it.
Oh, so something like this.
Yeah. Like what's the thought process in knowing what the epoxide
Okay, so the thought process is this. That's where what's today, Wednesday? So this would have been last week, I think, where we took the molecule and we said, okay, I'm going to color in the part of the molecule over here that came from the original molecule. So I've got 1 and 2. So this would have been, everything in blue came from the original molecule, right? And then I know I'm forming this carbon-carbon bond. So when you see that you've added something on and that you formed a carbon-carbon bond, that reaction screams Grignard. Right? Whenever you form a carbon-carbon bond, it's a Grignard of some sort. So then the question is, this part over here came from the other molecule, the one I circled. And this is where we talked about the idea that if the carbon-carbon bond that's formed is to the carbon with the OH on it, so the carbon-carbon bond I'm forming also has the OH directly attached to it, that was a Grignard plus a carbonyl. If the OH is 1 carbon away from the carbon-carbon bond I formed, then I need to react the Grignard with epoxide. Okay, so basically it would have been this negative charge reacted with the epoxide here, because the OH is 1 carbon away. Right. So usually what I would do then is I would just say, let me write the structure of that molecule, and then basically the OH had to swing over, and so this epoxide gives that molecule, right? Because when the carbon adds to the carbon on the left, the OH swings over. And that's exactly what's happened here. So if this is A and this is B, here's A, here's B. And the only thing I have to be careful of is that I added the Grignard to the carbon that's the least sterically hindered. And sadly, this is one, adding alkyl groups to the epoxides, this is something where there is not a yin and a yang. right? Normally CL, I can do it either way. Alcohols, I can do it either way. But right now, there's no way for me in one step to add the alkyl group to the least stabled. That I can do. I can't react it with the most stable. So this is one of those two. I don't have the complementary reaction.
Sorry, did you say that if the O is part of the carbon will be non-bonded?
So let's say the molecule, let's say it looked like this. Let's say it would have looked like that, where the bond that I just formed is now directly attached to the OH. That would have come from this. That would have come from that carbonyl. Okay. So that's how we tell if I give you a molecule and you got what Grignard do I need to add, or what molecule do I need to add to the Grignard? The way you can tell whether you need a carbonyl or an epoxide is where is the OH relative to the bond I just formed. If it's attached, carbonyl. If it's one away, then it's an epoxide. If it's more than one away, you're going to have to be really creative, because that's going to take more than one step. Okay? All right? So if you have questions, you can email me. I'll put this up and I'll make sure. I gave you back the homework assignments. I still have one homework assignment from Monday, and I put the answer key up for it. I don't know if I'll get it graded today or not. But if you have any questions, email me or come see me. Otherwise, I'll see you on Friday.
The one you gave us on Monday, we don't have to turn in.
What?
The one you gave us on Monday, we don't have to turn in.
Right, but the one that was due Monday is the one that's... Yeah, you turned it in.
Yeah. I didn't.
Which one?
The February 5th one.